Hi guys, welcome to question 2 of the 2016 electricity paper. Today we're going to go through, I'm probably going to cover part of question 2 in this video, or I might be able to get through the whole thing, we'll see. So, question 2, static electricity. In an X-ray machine, a heating element releases electrons from a negatively charged plate called the cathode. And then there's all this information here. So, the question is, calculate the electric field strength between the plates and state its direction. So there's two things we need to answer. So the electric field strength is just the voltage divided by the distance. So that's going to equal, we've got this 20,000 volts here. And then we've also got this distance that's already been converted to meters. So it's just simply 20,000 divided by 0.050, and that's going to equal 400,000 VM, or you could write it out as these 5 zeros, so 4 to the 5 V1. Now we're not done yet, we still need to state the direction. So in an electric field, it always goes from positive to negative. So we can write something like this, direction is positive to negative. Okay, so that would be from the anode, because this is positive, and to the cathode. So we can also go like anode to cathode. Alright, I think that's it. Okay, so this is a achieved question. So to get achieved, you need to have the correct voltage, and you also need to have the correct direction. Okay. State what type of energy an electron would have at the cathode negative plate, and what would happen to that energy as the electron moved towards the anode positive plate. Okay, so we're thinking about kinetic energy and electric potential energy. So if we think about it, the electron is going to have electric potential energy when it's in the negative plate, when it's at the cathode. As it moves towards the anode, it's going to gain kinetic energy. Okay, so we could write something like this. The electron loses electric potential energy and gains kinetic energy as it moves to the anode. So we could also talk about the electric field is like interacting with the electron, so that's how it loses its potential energy and converts to kinetic energy. So the electric field interacts with the electron, so it loses, we'll just call it EP because it's electric potential, and gains EK. Or changes into EK, whatever. Okay, so this is a merit question. To get merit, you need to have both the energy and why it happens. So merit is like a full answer. For achieved, you just need to have named one energy. So naming this and this, any one of them is achieved. Alright, next question. Calculate the speed of the electron as it reaches the positive plate. Okay, so we know from conservation of energy laws that EP has to equal EK. Now to find the speed we need to find EK, and to find EK we need to find EP. So we need to start by finding EP. So that's going to be, what's the form? Electric field strength times the charge times the distance. Now the charge is on your formula sheet, and it should be like 1.6 times 10 to the negative 19 if I remember, something like that. So what we're going to do is the electric field strength, which we calculated, was 4.5 times to the 4.5. I mean, not 4.5, just 4. 4 times 10 to the 5th times 1.6 times 10 to the negative 19 times the distance, which is 0.05. Okay, times 0.05. Okay, now that's going to give us our electric potential energy, which is going to equal 3.2 times 10 to the negative 15. So we know EK equals 3.2 times 10 negative 15 because conservation of energy. So now we have our EK formula, half of mv squared. If we rearrange that, that's going to become V equals square root of 2EK divided by m. So plugging in our values, we've got 2 times 3.2 times 10 to the negative 15 over the mass, which is also on your formula sheet. So that's going to be 9.1 times 10 to the negative 31. So you're going to get an answer of V will equal 8.39 times 10 to the 7 ms minus 1. Okay, this is another merit question. So the correct answer for the speed will get you a merit. Achieved is showing understanding that conservation of energy. So literally even this, just knowing this is enough to get you achieved. Or if you correctly calculated the electric potential energy, this is also achieved. Okay. In 1909, someone used two oppositely charged metal plates to keep a charged oil drop falling at terminal velocity, blah blah blah. This diagram shows the experiment. Discuss how it was possible to make the oil drop stationary between the plates. In your comprehensive answer, you should cover all these three things. So, I'm just going to label them 1, 2, 3, so we know how to structure our answer clearly. So let's start with number 1. So, identify the forces acting on the oil drop. So, we're obviously going to have a weight force, gravity force, and that's going to be pulling it downwards. Now, for it to be stationary, the forces have to equal, okay? So that means there has to be an electric force that's keeping it, that's pulling it up. So these two have to be equal, okay, for it to be stationary. So in our first bullet point, we could talk about what they are. So, the forces acting on the oil drop are downward weight force, which is gravity, and upward electrical force, which is provided by the electric field. Okay, that's bullet point number 1. So let's move on to bullet point number 2. So what's it asking now? Describe how the forces can combine to cause the oil drop to be stationary. Okay, that's pretty simple. We already talked about it. They just have to balance each other out. So these two forces, so the downward weight force and the electrical force, must be balanced. So the oil drop can be stationary. Okay, bullet point number 3. Explain what type of charge the oil drop must have in order to remain stationary. So it's either going to have a positive or a negative. Now, we know it can't be a positive because for the electrical force to be upwards, the type of charge has to be opposite to the charge on the top plate. Now, if we look at the top plate, it's a positive charge, right? So we know from our basic laws, like charges repel and opposite charges attract. Now, the force is attracting towards the positive plate. So that means the charge on the oil drop has to be negative, because if the charge on the oil drop was positive, it'd be going along this way, okay? So we know, so I can write, for the electrical force to be going upwards, the type of charge must be opposite to the charge of the top plate, which that's a positive charge. So the oil drop charge must be negative. I've covered all 3 of the questions. We've done that, we've done that, we've done that. So this is an excellence question. You can tell it's excellence because there's this word comprehensive. So for excellence, you need to have all 3 points, okay? You need to have explained that the electrical force must be upwards to balance the downwards force. And you also need to say the electric force has to be upwards, so the charge of the oil drop must be negative. So excellence is all 3 points. All 3. Merit is identifies the force and the forces must be balanced, so the charge drop is stationary. So merit is 2 points. Okay. And achieved is just identifies the 2 forces, or so any one of them. So achieved is any point. Right. Alright, that's question 2 done. I will cover question 3 soon. Cheers.